Hi, Daniel, can you hear me? Daniel? Okay, yes. You probably heard, right? So we have final exam open book. Okay. I don't know if you have any questions, just let me know. So you can use everything but your laptop and phone. Okay. No. Midterm 2 is online. Midterm 2 is online, so it is open book. It's open internet. Right? I'm talking about final. Oh, I know. I mean, I don't know what calculators you have in mind. Like, yeah, you can bring programmable. It doesn't really, like, the most you can do is, I mean, yeah, so you can bring your notes. That's exactly right. Okay. And please, whoever is watching this recording, come on Piazza, post your homeworks. Yeah, you can bring all your notebooks. Okay, bring your library. Bring all the books. Yes. Okay. Any more questions? I think the reason might not be posting is a lot of the problems aren't very hard. And the ones that are hard can be solved. Well, that's you. Another student was not agreeing with you and he was very upset. And then I told him to go on Piazza and he's like, okay. So, I mean, yeah, some problems are hard, and but please come on Piazza. I mean, some students already posted it. Yeah, just come on Piazza, make a private post, and I will help you. All right. We'll say I'm stuck and we'll do it together. You don't have to do it by yourself. Okay. So please, we're here to help you. Okay. Any more? All right. All right. So let's start with the final topic. I mean, this is not going to be too much in your final or midterm. I mean, not in the midterm, and maybe a question or something, some part in the final. I'm still trying to find some good homework questions for this. Just something simple. So, okay, calculus of variations. So far, we've been doing stuff over Rn, right? So we have this optimization problems, minimum of x in Rn, f of x, and g of x is less or equal than 0. Okay, these were the typical problems, and so, but n was finite. And the question is, what happens when n goes to infinity? Okay, can you still do optimization? So this shows up in many places. Of course, physics, you can do physics after a certain level without Hamiltonian mechanics. Okay, so we'll talk about that. And of course, neural nets, because data sets become massive. And so what you end up studying is called, I don't know if you like, Google this if you're interested, it's called stochastic gradient descent. And that's basically working with functionals, like we will do, okay? Because your data set is infinite dimensional. All right. Yeah, in finite dimensional, you have a finite set, finite dimension, sorry, Rn. But now we're going to study functions of functions called functionals. Okay. So just to, I know this is a bit abstract, so let me give you an example. Suppose C are continuous functions, okay? Okay. Then here's a functional. It takes the function u and it integrates it from 0 to 1. Okay, this is a functional. And if you remember from 2 to 4, these guys are linear. So you have f of a u plus bv is equal to a of integral of u plus integral of v. So you have a f of u and b f v. Okay, so these are what people mostly care about at some level. Anyway, so yeah, this is a functional, okay? So it's a function of functions. So yeah, integration, what's another one? Supremum, this is a functional, so take the supremum of the function. Okay. All right, all kinds of things. But for the most part, we will do our integrals. All right. So yeah, you have a functional over some function space, usually C1 or C2, meaning continuous with continuous derivatives. And we will write u dot just to show you that f is a function of the path. So this is not f of ux, this is f of u, because you're integrating over an entire 0, 1, right? It's not pointwise. Okay? Do you understand? Is that okay? Okay, good. All right, let's do an example. So here's your function space. Let me draw it for you. So you have 0, 1. And then it says that at time 0, you're 1. And then at time 1, you're also 1. Okay? So this is your function space, all these crazy guys. Could be all kinds of functions. This is another one. This is another one. Okay? There's a whole zoo of them. And then the functional is just integrating the function and its derivative. Okay? So this will be our example. And we will do a calculus of variations for it. So I will find the derivative with respect to u. Okay? So as the function varies, what happens to the functional? So at this moment is a good place to talk about variation of functions. So you already know continuous. So what was that? It was if you move a little bit, x prime is equal to x plus epsilon. Then you have that f of x prime minus f of x is less than some other epsilon prime, right? So if you move a little bit, okay, if you move a little bit away from x, then the output is also close, okay? That's called continuity. So we have the same thing for functionals. So if u of s tilde is equal to u of s plus some epsilon, and then vs, we'll talk about this. So you add some epsilon times some other function. Then by continuity, we mean that u tilde minus f of u is less than epsilon prime. Okay? So this is the comparison. Do you understand? Is that okay? Okay. So keep that in mind. I mean, yeah, so we're pretending, we are pretending that u is a point in R infinity. Okay, and this guy is in Rn. So you take some infinite dimensional vector, right? And you're saying that they're close. So, you know, the picture is, here's a U, and then here's a U prime. Okay, so it's very close as a graph. Okay, that's all. All right. So we want to minimize this, meaning what? I want to find some function in this space of functions that lower bounds all other ones. Okay, so suppose, let me ask you a question. Suppose U0 and U1 was equal to 0. Okay, what do you think would be the minimizer? What's your guess? Yeah, the 0, right? Why? Because this guy is non-negative, right? This is positive, right? So if you put 0, you get f of u star to be 0. Okay? Okay, but yeah, it doesn't allow you to do that, the boundary condition. Okay, so it's non-trivial. But if it was 0, then yeah. So if u0 equal u1 equals 0, then this is the minimizer. Okay, all right. All right, so yeah, we're gonna do calculus. So I need my Rolle's theorem. I need something that gives me the minimizers. So for that, I will need the following object called test function. So this is the thing I did before, where I had u tilde equal to u plus epsilon v. And why do I need this condition? Well, yeah, why do I need this condition? Because I want u0 to equal 1. Okay, so I want, when I perturb a little bit, I'm still in the space. I still have the same boundary conditions. Okay, so I think I write it after. Yeah, so the y here is because u of 0 plus s of v0 is equal to u of 0 plus s times 0, so 1. Okay, so even if you move a little bit by s, you're still in the space. Okay, all right. If you want to think of Rn, you want to take a derivative away from the boundary. So if you remember with simplices and all that stuff, we cannot take the derivative at the boundary because you need a neighborhood. So compare this to compare it to 1D taking derivatives over x minus delta x plus delta. You always need a neighborhood to take a derivative. Okay. All right. All right. Yeah. So suppose you have a minimizer and do your perturbation by this test function. Okay. So v at 0, v equal 1 is equal to 0. And yeah, since the guy is a minimizer, no matter how you perturb in the space, it's always the lower bound. Okay, so this is for all S. Yeah, for all S. So locally, you have something like this. You know, this is at S equals 0, and at other S, you're above it. Okay, so locally you have a local min, and this is the graph of the function. So this is a f of s. All right. But great, this is a 1D question. You just told me that f of 0 is a local min. And just from first year calculus, we know that this implies that the derivative at 0 will be 0. Okay. So yeah, back to first year. So I have to compute f prime. All right. So yeah, I wanted to do that with you, but maybe I'll do it. So f of 0. So this is f of u star plus sv minus f of u star. And this is 0, 1 u star plus sv squared and u star plus sv prime squared. Minus 0, 1 or whatever, u star squared, u star prime squared dx. Is that okay? So do you want me to do the cancellations? So, all right, let me do a little bit. So I will just do the first. So you see here, this is equal to u star squared, 2s v u star plus v s squared, right? And then since you divide by s, well, okay, let me not do that yet. So this guy cancels out with this, so, right? And this guy remains, so it's over here. And this guy also remained, and it's over here. Okay. Okay. And then I just divided by s, so that's how the s died out. Okay. Okay. So, okay, before I go into all the calculations, so let me just tell you where this is heading, because it's a bit too much. So what will happen is, yeah, so you take some limit, and eventually you end up with some ODE. Okay, so let me write it in this form. U star with some derivatives times v of x dx. All right. And this will be 0. So this is the goal. So this LU star, if I remember, it was something like, let me guess from here. So it's U star, and then you move one of the derivatives, so it's minus. So I'm going to prove this. I'm not doing it now. So this will be U star minus U double prime star. Okay? And we'll show that if this is true, then this ODE needs to be true for all x. Okay. And then we're back to ODEs, and I will give you the solution to this, is in terms of sine functions. Okay, so we'll get something like u of x, the minimizer is like sine of x with some constant. Okay, I don't remember exactly, we'll see it. I'm just trying to give you an idea. All right, anyhow, so let's get to that. We did this algebraic stuff, and what happens when I take limit s to 0? The left-hand side is f prime of 0, right? So that's what I want to get. So I can use my first-year calculus. Right, so I take s to 0, this guy is dead, right, because of this. So I'm just left with the first term over here. Okay. All right. Yeah, so it's a minimizer, so this is equal to 0. Okay. And now I'm gonna do the work to extract the ODE for it. Yeah, so we have to simplify this a bit. And I mean, okay, anyways, whatever. So we're doing, so again, let's go back. So I'm trying to simplify this. And the way I will simplify this, I will take out the derivative from the V prime. Okay, so then I can factor out the V. So how do you do that? Well, integration by parts. So that's how you move a derivative from one function to the other. Okay. And then can someone tell me why this is equal to 0? Any ideas? Yeah. Yeah. So V of 0, V1 is 0 by definition. Okay, that's how we pick the V. All right, so this guy is dead. So, yeah, so you have this. So the condition we had before, the F prime, the F prime equals 0 becomes this equation over here, this beautiful equation. Anyhow. All right. So now I'm going to prove the following. I'm going to prove that since this is true for all test functions, I mean, it could be anything. You get that this this summation, this u prime plus u double prime, has to equal 0. Okay, so here in this equation, let g of x equal u star x, and then u double prime star x. Okay. Whatever. All right. So, I mean, you don't need to know the proof because it's a little bit into analysis, but it's in the book, so I thought I should do it. So again, suppose your guy, if you integrate it with all kinds of functions, is 0. Let's show that the function itself is forced to be 0. So the way I visualize this is as follows. Suppose g of x is like this. Then you're saying no matter what you integrate with, like this v-axis, you always get 0. But the point is, if you keep covering all the graph, eventually you cover all the area under the graph, right? And so so you end up with G actually being the 0. That's my picture of it. All right. But the proof is much simpler. It goes by contradiction. Suppose not, suppose G is not 0. So there is a little location somewhere where you have a little bump. Okay, so G of X naught is strictly positive without loss of generality. But then by continuity, you have the following. You have that a whole neighborhood is positive. Does anybody know how to get this? Or, well, I mean, you probably, yes. How do I go from a single point being positive to a whole neighborhood? Any ideas? Yeah, well, do you know how to use continuity here? I'm just curious because we've done this argument like maybe 4 times. Greater. Yeah, okay. So yeah, let me use all your notations. So first, like you said, take G of X naught to be bigger than lambda over 2. And then take epsilon, right? Epsilon neighborhood. So take epsilon neighborhood. So you have X minus X naught less than epsilon. Oh, X naught. So take this one such that what do I want? I want G of X minus G of X naught to be, let's say, less than lambda over 4. Okay. I mean, I don't know, you can pick your coefficients, but then let's move this around. What is it saying? So I want a lower bound, right? So how do I want this? So I have G of X naught minus G of X less than lambda over 4. So you have G of X is bigger than G of X naught minus lambda over 4, which is bigger than lambda over 2 minus lambda over 4, which is lambda over 4, which is positive. Okay? Is that okay? I mean, this is a frequent argument, so it's good to know it. We've done this. This is the main argument we've done throughout this course, actually, like theoretical. All right. And I mean, pictorially, yeah, pictorial is what we said. So you have your guy is has height lambda over 2, and it says just take a neighborhood where the height is lambda over 4. And this distance is epsilon. Right? That's the picture. That's all. So you stay within this blue region. Okay? Okay. Oh, you let the point be some epsilon and take delta to get an epsilon over 2. Yes. That's the usual notation. Yeah, you have to use your, I don't care, it doesn't matter, it's fine. Yeah, thank you, Daniel, exactly. Good. I mean, it's called delta epsilon. It's not called lambda epsilon or epsilon lambda. Anyways, so Yeah, so you can find the neighborhood where your guy is strictly positive, but then what do you want to say? It's possible to find functions as the Vx strictly positive. And yeah, so here's the stupid example. Suppose, oops. So take this to be C, take this to be D, and then take the bell curve in between, okay? That's an example. So I can even give you the coordinates. So when C is 0, so it's something like this, 1 minus x. You can check. Okay. Oh, with a minus, right? Okay, let me do it. Let me do it. So suppose C is 0, 0, 1. You can do the translation yourself. So what do I want? I want it when it's 1, you get 1 over 0, so it's infinity. So I want the minus. And then when you have 0, just do it times. I don't care. Like this. Yeah. So when x is 0, yeah, so pick this guy. Okay? I don't know who cares, but I like it. Okay. Which one? E to the 1. But what about 0 though? When it's 0, okay, anyways. You need it to be 0 at the thing. Anyways. Okay. All right, so what happened here? Take this neighborhood that we talked about, x epsilon, x0 minus like this. Okay. And like Ben Ruiz said, this guy is bigger than lambda over 4. Okay. And this guy is also positive. Let's say lambda squared over 4. I don't know. So you can pick the values. If I can I can make it times lambda to get the thing. But anyways, this is strictly positive. But then this guy told us f prime of 0 is 0. Okay, so you get a contradiction. Is that okay? So that's how continuity is used for contradiction. You can just apply f of x minus 1. Yeah, Daniel, let's talk about it at the end. Right, so you are not allowed to have g of x to be non-zero, so it's 0 everywhere. And so lo and behold, we get our ODE. There should be a minus in all the other ones. I don't know why I forgot. Okay, so again, our guy was, I will fix it later, I'm sorry. So it was this u double prime Vx dx equals 0. And then from our lemma, which has a name, what's the name? Fundamental theorem. Okay, wow. From FOC, you get this equation. I don't know. Okay. So we're back to ODEs. Of course, it's not a prerequisite, so I'm not expecting you to solve ODEs, other than what would be in homework or in the slides. Okay, so I will not put ODE that you haven't seen. Okay, I'm just not allowed to. And this goes under the name Euler-Lagrange. Okay, it's a very big. The first thing you come around when you go calculus of variation, that's the guy. That's why we study it. So this is our ODE, all right? So this is your system. It says that its second derivative is equal to the function, and you have this boundary data. And the way usually you solve this is with an ansatz. So this is called an ansatz, meaning you you assume that your function looks like this, and then you figure out the constants that will make it work. Okay? So why did we pick this guy? Well, because the exponential is the guy who's equal to its own derivative. So we're like, if you take derivative twice, you still have exponential, right? So that's the intuition. So we picked it because e to the x, sine of x, cosine x, repeat after taking after d squared. Okay, after double derivative. Okay, all right. What we're doing now was covered in PDAs in higher dimensions. Yeah, I mean, this is what we're doing, you know. Right, yes. There's a PD version that we'll do on the last week of classes. But of course, you will not be tested on it because you haven't even done ODEs, some of you. All right, so how did I get this system? Let me explain. I mean, I think it's kind of obvious, right? So I plug in U of 0 and I get C1, C2, right? Because it's like e to the 0 and e to the minus 0. And then that's how I get, yeah. But this is a 2x2 system, and I have two equations, two unknowns. I solve for them, and I get this solution. Okay, that's it. That will be the hardest kind of ODE you might see. I mean, it's not really anything more than that. We will also do sine and cosine, and that will be it. Okay. All right. Yeah, I mean, I don't know. People haven't really seen this, so I can't go too deeper into this, but there is an existence and uniqueness. This is a good point to mention it. So in general, here's the theorem. You have d dy dt. Y is a function of time, and suppose it equals some f of t. All right. If f, yeah, let me just say it, and then you'll complain. If f satisfies the following condition called Lipschitz. So f of x minus f of y is less than L x minus y. Then star always has a unique solution. Okay, this is called, yes, fun times. This is called existence and uniqueness for ODEs. I mean, it's the basis for like all of physics. You can't do PDEs unless you have this. But okay, so this is the theorem, and yeah, so that's nice. Why is it nice? Because it tells you if you start with a functional, so where is our, yeah, so we started with some functional, and then we use the first order condition. To get the following equation, u star minus u double prime v of x dx, right? And this is beautiful because you will always get ODEs. I mean, that's how it is if you have an integral of this form. So the theorem tells you that you will always have a solution. Okay, so that's the beauty of this ODE result. Okay, anyhow, so right, one thing I have to say. So we found the minimizer. Again, what's the minimizer? Your minimizer will be u of x equal to c, no, let me write it. 1 e plus 1 e to the x and e plus 1, or if you like, x plus 1. Okay, that will be the minimizer for that functional. Okay, so the functional was, I'll just show you the functional in case you forgot. So this is the problem we were trying to solve, and we found that this is bigger or equal than f of, let me write it again, x e plus 1 and 1 minus x, right? Yeah, I forgot. Okay, so this would be the minimizer for all these guys. Okay, good. Meaning if you integrate it, blah, blah, blah. Okay. One problem is that this only gives you a candidate, but you want to have a unique minimizer, sort of a convexity condition, like like we did throughout this course. You want one minimizer, so you check the second derivative, right? So I mean, there is stuff of second variation, second derivative, but we will not do this. This is way beyond. So we will only do a first order condition in this course for this stuff. All right, so let me prove to you that there is a minimizer and it will be the unique one. So yeah. So all you have to do is perturb. So we perturb. And then, but your guy was an integral, so you just expand out the integral. Okay? Is that okay? All right. And we just proved that this guy over here was 0 because of f prime being 0, the first order condition. And the second term is non-negative because it's a summation of squares. So you end up with that any perturbation is an upper bound for your minimizer. So note that I didn't have to use my specific minimizer. This is a general property of this functional. And another way to think about it is that you have convexity. Because this guy is dead, if you take double derivative in S, what do you get? What's the double derivative? Huh? Yeah, so, and then what do you note about this one? Yeah, so you have convexity. Okay, so that's why you have unique minimizer. Okay, good. So you can do it that way as well. All right. So yeah, I'll take a break because it's a new topic. All right. So yes, let's start. Um, the I'm Greek and I can't even pronounce it, so I don't know. Uh, Brachy something, brachychrone, brachystochronos, or the fastest time. Anyways, this is the first problem where calculus of variations started. Yeah, that was the very beginning of it, famously solved by Newton, anonymously, but yeah, Bernoulli said, I can tell the paw of the lion. So yeah, this is a very famous problem solved by one of the best physicists. The problem is very simple. That, so you have 2 points in space, A and B, and you have gravity. You know what? I might as well show you the clip. I don't know why I'm talking. We have YouTube. So brachychrone. Oh, brachyst. Experiment. Yeah, whatever. I don't care what you have to say. So you have 2 points in space, A and B. And the question by Galileo was, if you consider all the various paths, so you have one on top, bottom, straight line, uh, you know, swimming pool slide. So you have all this, and the question is, which one will go the fastest? And does anybody know which one will go the fastest to point B? Which curve? The blue, the yellow, green, orange? What do you guys think? Which one will go the fastest? How many think the yellow? Ah, how many think the blue? Nobody thinks the blue? Okay, let's see the old man. Yeah, maybe it was too fast. Oh yeah, here. You see the blue one? Did you catch it? Did you see it? Okay, good. Oh, they did it in high school? Or, oh wow. Um, okay, let me see. So yeah, let's figure out why. Why is it the blue one that will go the fastest? And you cannot do it with calculus, surprisingly. You have to go into this 4th-year course. So let's do it. I'm gonna do it. It's gonna take 10 slides to prove that it will be the blue one. It's crazy. All right. First, let's put mathematics. So what you want is a curve that goes from point A to point B. All right, so this is point B in the Cartesian plane. So on the y-axis, and you end up in the x-axis, or what? Oh, it starts. Oh, I'm sorry. 0A and B0. Okay, and these are your points over here, and you're going through all the possible paths that connect the 2 points. Okay, and now I have to bring gravity in. So yeah, I want C0 to be A and CT to be B. You write it in Cartesian coordinates. To make our life a little bit easy, we fix one of the parameters and vary the other one. So it's truly a graph. So think about it like this. This is x of t. And this point over here will be x of t, ux of t. Okay, so you have one unknown. You don't want to have two, too much work. So we have only one, because after all, we just want a 1D curve. So, and yeah, okay. So the velocity, you can use chain rule. So that's what happened over here. And we factor out the explain. What do I want? I want x of t. That's what I want. All right, so now I have to bring in the constraints, otherwise just take the straight line, who cares? I have to formulate a functional that contains the Brachistochrone problem, okay? So I need to formulate for you the minimization problem. So going back to high school, this is the velocity. So this is the kinetic energy, and this is V. So let me explain what happened here. Norm of V squared is equal to, x prime squared plus this, u prime, x prime squared. Okay, and then we just factor out the x prime squared. Okay, that's how we get this expression. You also need potential. So potential is the following. It's the height. So if I push you off this desk, you won't get hurt. But if I push you over the Eiffel Tower, you will die. And that's because of the height. You accumulated a lot of energy. So you die very badly. Yeah. So this is the height, and you have a basketball. And the higher you put it, the harder it will hit. And then move up. Yeah. All right. We will use the following beautiful result that t plus v in time is a constant. Okay, and we will use that it's equal to the initial time. Okay, and through this you get your functional. So you will see in a second. So yeah, I just added them, nothing new. I know that my guy is constant, so here we use conservation of energy. Okay, and why is it equal to this? because t of 0 is 0. Why? Because the initial velocity is 0. So in that clip, your ball starts with 0 velocity. Okay? So that's why there's no t0, no kinetic energy. Okay. So now you combine, where is it? You will combine this side with this one. So these two are equal by conservation of energy. So I'm not going to do all the calculus, but you just move it and you get this two, okay? Is that okay? Okay. So this guy is equal to, anyway, so I just combined the two. All right, so now coming back to our problem, what I want is, I want to minimize the time it takes to go from A to B, okay? So, in other words, you want to do the following. So you integrate over time. So this is the trick they're talking about. And you sub in the expression for x prime. Okay, so again, this is a mathematical trick, but this guy has meaning. So we'll come back to it. But yeah, you'll see how this is used. What shall I say? The goal of the Brachenschrone, whatever, is to minimize this quantity. You want to minimize T. And so but T has a lot of content in it. It's very abstract. So what we do is we bring in X prime. And this is just a dirty trick. Here they're using that X prime T over X prime T is equal to 1. Okay? It's just a dirty trick. Because all I need to know, how does T depend on X of T? I need to know so that I can, how do you say it? So T is my functional, right? Capital T is my functional, and I need to know how T depends on the trajectory. So I need to know how time depends on the on trajectory, right? Okay, and so you do this dirty trick, but then you use your expression from star. Okay, all right, so now we're here. Now we have to use second year calculus. So we moved from high school to second year calculus. So now this last quantity is called the line integral. Remember a little bit? Okay, so what is a line integral? It's a function of this form where you have a trajectory in space and you cut it into pieces. Okay, so this is equal to x of t0, x of t1, f of z. Okay, so this is a line integral. You integrate along the curve. Okay. Yeah. Oh, this would be capital. Wait, what? Oh, this is what? So f prime is equal to f. Okay, so this is capital F prime. All right, I'll fix it. So this is capital F which I do next. Okay. Anyhow, so right. So we do reverse chain rule. Okay. Why? Because dt of f of xt is equal to f capital prime times x prime of t. Okay. Is that okay? All right. Then you use the fundamental theorem of calculus, FTC. Okay. So you just evaluate the endpoints. And you got your AB. All right, because we know that the boundary condition is that you hit B at the endpoint and A at the beginning. Okay. All right. So how does this all relate? Well, let's come back. We had, okay, no, too quick. So let's go back to so we had this integral and we call this f of xt. Okay. And using this line integral formulation, you write it as a to b. I will show you in a second in terms of dz. Okay, so I will write this like this. All right, let's go. So yeah. So we wrote wherever you see x of t, we plugged in x. So that's all we did. And then we use our boundary conditions. Okay, fine, 0b, yes. So this is our boundary conditions. All right, so here's the brachichrome problem. Is minimize the time, because this is time, over all trajectories from A to B. Okay? So again, the logic is simple. You want to minimize the time it takes to go from A to B. We did this dirty trick of writing t like this and then bringing in x prime of t. And we express this as an integral, and using Newton physics, we remove the derivative, dx prime. So using Newton physics, we wrote a nice expression for the trajectory derivative. Okay. All right. So this is the problem. So now there's no more physics; it's just math. Well, I mean, for intuition, it's good to go back to physics. We have to minimize this. This is a functional. It's a terrible looking functional. It's nonlinear. We're screwed. So we're going to do the same business. Suppose that you found the minimizer. We don't know how it looks, but suppose you found a U star connecting A to B. Then you know that this time functional will be minimized over this trajectory. Okay? Over all perturbations. All right. And from first year calculus, we said that this is nothing else but that f prime of 0 being 0, right? If I call this f of s, right? So now this is something that you need to be able to do. You will have some functional, and you will need to take the time derivative and set it to 0. Right? let me do like a stupid example just to show you, like, suppose you have something like, I don't know, some crazy power, USV cube. Then, yeah, DDS will be what? So you have a 3, and then you do chain rule, right? You get, what do you get? You get SV, no, you get V, right? Or no, this is DX, right? And then you set this to 0, and you get U square V. Which, by the way, if you set, I'm curious now. Suppose you set this to 0, you can probably get it. Oh yeah, this is way too easy. So what do you think is the minimizer? So remember that theorem, right? The theorem said if you have g of x vx equal to 0 for all v, with v0 1, v0 0, v1 0, then g of x is identically 0. Call this FOC, fundamental theorem of calculus of variations. So what do you think FOC tells you? Who's the minimizer? Huh? You get u square of x to be 0. So the minimizer would be just the 0 guy. That's it. Okay? Simple as that. That's all. Yeah. So yeah, I will assign questions for this week and like next quiz that are just this. And then for next week, it would be multivariate of this. So you get PDEs. And that would be it. I mean, there's nothing more we can do. Yeah. All right, we'll see. Okay, so yeah, shall I do it? It's too ugly. So if you go back to this, so over here, right, you have this terrible looking functional, and you plug in S. So it would be like 1 plus U plus SV prime squared, and over, let me do a half like this, over 2 times gravity times A acceleration U minus SV. Okay? And then you take derivative in T, which is a rational function, and it's okay. So what? All right. So you take I don't know, there's a lot of meat here, but it will be too much. You won't be tested on it, so I don't know if I want to do it. So if you take derivative in S, it turns out that you can rewrite this as follows: 1 plus U prime squared, and then A minus U star minus 1. So let me do it here. Smaller writing. So U prime squared, A minus U C minus 1. All right. And you set, and you multiply it by your test function. And you set it to 0. Okay, so I'm not going to do this. It's all disgusting. But if you do all that rational function stuff, you get this, and you do integration by parts, and there's a lot of stuff. You won't be tested, and so I'm not. So you do that, and the goal is always to isolate V of X. Okay, and from here you get by FOC, the fundamental theorem of calculus of variations, that the minimizer, if it exists, it has to satisfy this ODE, which is a nonlinear ODE. Okay, it's called the Euler-Lagrange equation for your minimization. All right. I mean, I should put some related. Anyway, so again, we have an ANSAS. So so this is your ODE, and the way you usually solve ODEs is you say, okay, I think the solution will look like this. And then you figure out the A and K. So remember, before we had C1EX, C2E minus X, and we found the C1, C2. Same thing here, we will find A and K. Okay, all right. So I start taking derivatives. So I take derivative of this. I get minus K sine T, because cosine prime is equal to minus sine. Okay. Then you take, what else? Sure. Yeah, so I have this expression for U prime, the Euler-Lagrange over here, and I plug in whenever I see U prime, I put in the expression we got. So I get this over here, and I plugged in U over here. And this whole thing is equal to 1. Yeah. Then, okay, what else? What did I do? I simplified. All right, fine. I canceled out the A's. Yeah, okay. Anyways. Now I'm just trying to solve for x prime of t. So I'll just skip to that step. So I have x prime of t squared. So where am I? Anyhow, so you have this x prime of t on the right is equal to some crazy looking trigonometric. And what else? Right. So the signs cancel out, and I have an x prime. So now I have to take derivatives, but when you take square root, the left-hand side is positive. Can anyone tell me why the right-hand side is always positive or no negative? Yeah. So that's why there's no absolute value, which will make life harder. So this is your curve. So that blue guy is this. And you know what? I don't trust myself, so let's put Wolfram alpha. So come back. So this is what's my choice for K? Where is it? Yeah, okay, what is K? I don't care. I'll put some numbers. Let's put T minus sine T. Yes. And then Anyways, so that's the curve. Okay. And it goes from 0 to 1, right? So for t 0 to 1. Anyways, whatever. xt is the, that's right. Yeah, so yeah, it's a little bit harder than that. So let's do it. I have to plug it into our, so it will be this. Okay, let's do it. Oops. So this is the displacement, and this is the height. Take trajectory to be 1 minus 2 times 1 minus cosine t. I don't know, it's kind of hard to visualize. Okay, anyways, moving on. Yeah, xt is the displacement, and then you need to add the height. I'll do it on Thursday. I'll do it on MATLAB. I thought I could do it with Wolfram. All right, so we found the displacement. And now let's figure out the constants. So you have some boundary data. When x of t is 0, at time 0, you're at upstairs over there. And then at b, you're down here. So yeah, anyways, this is your trajectory. So it will be like this. This is c of t. So it's a little bit hard to visualize. So x is this, and this is the y, the height. You know, at time equals 0, you're supposed to be point A, and at time equal B, time equal T, you're supposed to be B. And yeah, I mean, let's say, I don't know, suppose you start from 0, 1, and suppose the other guy is 1, 0. And let's find the points. So C0 is equal to 0, and then A, so that's okay. And from here, you ask k t minus sine t to be 1, and a, so let's say 1 here, to equal 0. Of course, this is a non-linear system, so you have to use your calculator with Arcos to get it. You can just solve it like that. But 2 equations, 2 unknowns, and you can get it. All right. Okay. So how many slides? This was like crazy. Yeah, we start from slide. Yeah, slide 15, and then we went down to 23. So it's quite a bit of content just to state the amazing result. The guy given gravity. So gravity is the only force. There's no initial push. given only gravity, the fastest way to go from A to B is through this curve given by sine and cos. Okay, this is the fastest trajectory going from A to B. This is B and this is A. Beautiful result. And you can only do it with calculus of variations. That's why it was invented, to solve this problem back in the 1600s. All right. So let's make things a little bit more formal so you can have some results you can just reference instead of doing this over and over again. This is your function space. Okay, we're just gonna have C1 always and two boundary data. So there's nothing else. We're not gonna go anywhere else. And your functional will always look like this. Okay. So like in the homework, this will be some function of the u and u prime, not double prime. We're not gonna do that. So that means since you have this guy over here, you have to do integration by parts. Okay. Why? Because when you plug in your perturbation, you will have v prime, and the v prime needs to become v, right? Okay. And coming back to our stuff, this is called the Lagrangian. And yes, this is exactly what you will get if you discretized this integral. You come back to Rn. So maybe I should talk about this. Let's see a little bit. It might be too much. That's okay. It's too much. That's fine. Now we're gonna get you the Euler Lagrange. So instead of you, for the first homework, yeah, you have to do it. And it might be like part A. But you can always check yourself. I'm guessing a good question is find the DDF/DS, get Euler Lagrange, and compare it to just using the class result. And do you get the same answer or no? So I'm going to derive for you the ODE. All right. Anyways, so we use this notation, LZ, to mean partial with respect to velocity. Height. And then with respect to momentum. Yeah, so anyways, in case you see this elsewhere, they call this momentum variables in physics. And they call this guy velocity. All right. Okay. So here's a beautiful object. Suppose that you start with any functional. You can always, always start from the left-hand side and write it in this form. Okay? And that's because you can always use integration by parts. So we will go over this. So anyways, suppose you can do this, then from the fundamental theorem of calculus of variations, this guy G will be called the variational derivative, is also called Frechet, and is also called, what was it? I forgot. There was one more. Garbeau, yes. Anyways, whatever you come across. And these guys are all equal to the function g. Okay? Is that okay? I want to do an example. The analog of this guy is the gradient. So, yeah, this is g of x over here. And compare this to what we talked about on second week, the directional derivative. In direction v to vector v is equal to the gradient of the function times v. Let me ask you a question. What happens when I take v equal to the gradient of f? Any ideas? Oh, no, no, no. This. What did we say about this direction? Huh? What? So if you plug it in, you get, what do you get? You get that this guy, dds of f, is equal to f squared over this. So you get the norm of the gradient. And this is called the greatest increase. Okay. And you should try to think about this the same, that here, if you take v of x to be your variation, then again, it points to the greatest functional increase. Okay? All right, good. Yes. So what? Oh yeah, I don't, oh yes, my example. So the example we had was what? F of u is equal 0, 1 u squared plus u prime squared dx, okay? That is the one we talked about in the beginning of class. This is your functional. So the Lagrangian would be this guy. So you put, wherever you see u, you put z, and wherever you see u prime, you put, there was a half. Okay, I'll put the half. You put p equal u prime, okay? You'll see why we need this. So this is your Lagrangian, and I'm going to derive the ODE. So you don't have to do it every time. You can just use it. So again, this is our functional. And through hard work that you won't need to do, because you're going to have the result. I mean, maybe like part A, so we'll see. We derived the variation. Okay, we call this g of x. We also call it df du x. Okay, this is called functional derivative. This is the first time you see this, some of you. And it just means that you take derivative over graphs. So you have u and then you perturb by u plus SV. Okay? And yeah, okay. And we call this g of x. So here's the result. Suppose that you are variationally differentiable, functional differentiable. Then if you set this guy to 0, you get your Euler-Lagrange. I think I say that here, no? Yeah, so let me say it here. So this is just the Euler-Lagrange. Okay, so if you come back to it later, you know what's going on. And yeah, we set this to 0 and we had u squared, sorry, u prime minus u double prime. Yeah, this was your ODE and we solved it. Then we got u star, the minimizer was ex 1 plus e plus e to the 1 minus x 1 plus e, right? Okay, yeah. So that was the minimizer we got. But so what I'm going to prove to you is I'm going to prove to you, no, keep it. I'm going to prove that this is always equal to 0 if u star is a minimizer. Okay, so if you're a minimizer, then you have your derivative is 0. This is like first year calculus, right? If x star is a min, local min, then the derivative is equal to 0 at x equal x star, right? That's all we're proving. Yeah, nothing else. Okay, let's go. You do your perturbation, and it's a minimizer. We let this function to be f of s. And we know that if you take its derivative at 0, it's 0 because it's a minimum. Okay. So now here. So so yeah, this is equal to f prime 0, which is 0 because s is local min. But then, can someone tell me how can I deduce that the variational derivative is identically 0? What result am I supposed to use? Any ideas? Anybody? Zoom? Does anybody from Zoom know how can I get this result? Yeah, let me see if anybody else. Anybody? Going once, going twice. FOC, thank you. So this is, you can always just mention it. The TA will know. So this is called fundamental theorem of calculus of variations. Let me remind it for you once again. It says that if you have g of x, Vx equal to 0, for all Vx that satisfy V0 equal V1 equal 0, then g of x will be identically 0. Okay, so this is called FOC. Okay, good. So yeah, using calculus variations, we get a result. So yeah, going back to first week, we had that being a minimizer implies zero gradient if you're on the interior. So this is only in the interior. Oops. Okay. Because at the boundary, all you can guarantee is that the gradient will be non-negative. I don't know if you remember, but that was the condition. It has to be interior, otherwise it doesn't work, right? You may. So yeah, here we have a similar condition. We set the variational derivative to 0. So yeah, you have some functional, you have a Lagrangian function, and you can use this result as much as you want. So I'm going to prove to you that the variational derivative is always equal to this. So by setting this guy to 0, you get your ODE, okay? All right, so you don't have to take time as derivatives, set them to 0, none of that. You start, let me do it on the side, the example. So we had this guy, right? U squared, U prime squared, like this. You consider the functional given by x, z, p equal to z squared, p squared over 2. And then I follow what happens here. Dx is 0, so dl dx is 0, okay? Because it has no x. And dl dz is equal to what? Huh? No. Whatever. What? I heard 0. Oh, I'm sorry. I was like, what? Yeah, it's z. Yeah, thank you. And then you set this, so you get 0 plus z. Oh, sorry, u of x, okay? Because you plug in z. And you set this guy to, wait, what? And you set this guy to 0. Something's weird. Okay, well, I'll see what I typed, and then we'll come back. That's bizarre. Z, no, yeah, it is Z, it is Z. I heard 0. Anyhow. So this is the Euler Lagrange, and I want to see the example, then we'll finish class. Where is my example? Yeah, is that something else? Whatever. Anyways, we'll do this next time. Okay, thank you. Bizarre. Oh, wait, what? Ah, yes. Yes. Oh, I see. All right, anyways. Okay, I'll tell you. right? You evaluate LP, which is P, you find LZ, which is Z, and then you plug in LP to PV prime, so you get your double derivative. Yeah, you take P derivative, so you get P, and then you plug in P equal to U prime. And then you take dx derivative with it. Is that okay? Okay. We'll do it again next time.